Alright, inclined planes. So this is your last video for Newton's laws. I'm just going to go through quite a bit of scenarios that you may or may not come across in a test or an exam, but I'm going to try and do as many as possible so that you have a better idea of what we mean by terms like inclined planes. So when I'm talking about inclined planes, all we're talking about is that the surface is at an angle. It is not parallel to the earth. All right. Now, when a surface is at an angle, these two images above here, what we're looking at is what would be the object's motion if you tilt that surface. So incline just means we're going to tilt it. Right? Now, depending on the type of angle, that will influence what happens to an object. But naturally, if I think about any object that I put onto a tilted surface, I know that naturally, this object will want to do this. So the natural motion for an object on a, oops, I have to switch colors. Tilted surface is to slide down. Right, so it wants to come back here to the ground point. Right, that's its natural motion. Now the rate at which it slides down, right, down that surface is dependent on how tilted the surface is. So if I look at this little scenario over here, and I look at these angles here, so I could say, for example, that that angle there may be 30 degrees. And this angle here may be 45 degrees. But as you can see here, in option A, sorry, option B. In option A, it's because the angle is smaller, it is easier to move this incline up the tilted surface. The bigger the angle is, the greater the difficulty. So we should write that down. We should say that the rate therefore, the greater the tilt, or rather angle of the surface, the faster the rate at which the object will slide down. So now if they talk about angles, then you can mention that if the increase is an increase in the size of the angle, then there's an increase in acceleration. All right, so when we're looking at a tilted surface, we're actually looking at an inclined plane. Right, now, objects are known to slide down, they'll accelerate downwards, inclined planes, because of unbalanced forces. So to try and understand this type of motion, it's important to analyze the forces that are acting on the object. Now, if I have an object, right, that is on a surface, right, any object on any surface, then I'm stuck in this situation where I've got two forces acting on this object. Because of the object's mass, it must experience some sort of gravitational force towards the center of the earth. And because it's on the surface, and we know from Newton's third law, there must be a force that's going the opposite direction of gravity, which is the force of the normal. So I know that naturally these are the forces if we are parallel to the earth. Now what's happening now is if I introduce an angle to the surface and I tilt the surface upwards, now I'm left with this like setup here. Right? That's my new surface. And I've got my object on that surface. Then the game changes a little bit. Because if I'm not parallel to the earth, then whatever my force of gravity is, especially my force of gravity, it needs to compensate for that increase in this angle. So if I'm looking at inclined planes and I'm looking at something on an incline, then my situation is that my forces of gravity, or my forces of gravity according to Newton's laws, is if I'm looking at the original image, right? If I'm looking at the original image, I have this force that's doing this and pushing down on the earth. The earth is doing the exact same thing and pushing back up. Great. It's on the surface. There's no break there. But now when we put something onto an incline, I have a different sort of situation, because now I have this angle here, and the force of gravity in these situations is not acting on the object, but now it's acting on the angle. So in inclined planes, the force of gravity acts on the angle, not on the object. So how we represent a force that's on an incline, or a gravitational force on an incline, is much more different than a gravitational force on a surface that is parallel to the earth. So we're just going to have a look at that sort of setup. Now, not forgetting that these objects that we put onto inclined planes are still on a surface, which means they still need to have a normal force. So remember, when we talk about the normal force, I know that the normal force, or the notation Fn, is always perpendicular to the surface. Alright, I'm going to use this perpendicular sign. Oops, let's put it underneath here. Right. To the surface, no matter which way the surface faces, and also no matter the angle. So when we draw the normal force in these types of diagrams, whatever the surface, they must be perpendicular to the surface. So if I'm looking there, perpendicular to the surface. If I'm looking here, perpendicular to the surface. So don't forget that normal force, especially here, we're looking here, with inclines, will not be in that manner any longer. It has to move with the angle. So essentially then, if I'm looking at these different types of normal forces, what happens to the force of gravity on an incline? Now, I know that gravity, right, in any situation, must be directly downwards. So if I'm looking, just bring this up, amplify it. Right, so if I'm on an incline, this is what my force of gravity looks like. But like I just said to you now, that the force of gravity here on an incline, right, acts on the angle, not the object. Now, if something like that happens, right, if a force directed at an angle, this is the rule, must be resolved into its horizontal and vertical components. So when I'm looking at this force of gravity here, I'm going to take my force of gravity as F rays. Right? And essentially speaking now, I have Fn here, right? And that's perpendicular to the surface. And exactly perpendicular here, I've got another force. And I also know I've got a force here that's going to go down my incline. So the one force here is called F parallel, because it's parallel to the surface. And the other force is here, and this is called F perpendicular. So I can't keep my force of gravity going downwards. I have to sort it into its components to do any form of calculation. So your Fg essentially becomes your force parallel to the surface and your force perpendicular to the surface. All right. So when I'm looking at it then, I'm looking at this sort of setup. So that's the idea that we're working with. Now, if I think of inclined planes in that way, or if I think of this setup like this, I want you to imagine it like in this situation. Right. If I remember, if I think of an inclined plane, right? This is my inclined plane. And of my inclined plane, just move this. Sorry, just put this out of the way. Of my inclined plane, I know that I have a 90-degree angle here. And let's say I've got my object over here. Right, so that's my setup. I also know that going upwards in this direction, I've got the force of the normal. And I know that coming down this way, I've got force of gravity, or rather mg. That's my gravitational force. But I also know that when an object is not parallel to the Earth's surface, I have to use components. So what I want you to imagine is, if that's my setup, and when I put in my components, I want you to just have a look at this. I know that my object on an incline is going to want to slide down. So I've got to get that sorted out. Alright? So I've got my force applied there. And my force applied is Fx. Alright? I'm going to show you now how this works. Because then you can turn it around and be like, why is it not Fy? And then I've got this force here, parallel to my force, perpendicular to my force of the normal. And that's Fy. Now, essentially, if I'm looking at that kind of a setup here, if I had to draw a triangle, so I'm just going to get another color and draw it in orange. Oops. Okay. Now, when I'm looking at my little setup here, I know that I've got F rays here. So I'm just going to go with this orange color. And this orange gives me F rays. Great. When I have F rays, I know that over here, I have a force that's doing this. Oops. And that's my Fy. And coming across, let's just extend this, doing this is Fx. And technically my 90-degree angle is there. So there's a connection between, there's a connection between my 90-degree angles. So when I'm looking at my incline itself, then I must understand that if I put an object on the surface of that, this is how my whole triangle kind of rotates itself. So where I would have had an angle there, angle theta, my angle is actually angle theta there. So there's my two angles and how they related to each other. So when I'm looking at this type of setup, I must make sure that I draw my MG and my FN. Then I must draw in my opposite and my adjacent. My opposite goes perpendicular here, like that, right? And then I must draw my F parallel to the surface of the incline that forms a head to tail kind of diagram. So look, each vector follows the next vector, and I've got myself a bit of a close triangle, right? Your angle is always going to be, so theta will always be between F res and MG perpendicular. So here, right? So essentially what's happening in these sort of setups is we need to resolve into components. Now when we talk about resolving into components, they come with formulas of their own. So when I think about those formulas, I know that Fg is going to give me mg, right? Which is great. That's my gravitational force. Right, so mass times gravity. If I want to sort something into this x component, then I'm going to say the x component gives me mg sine theta. Oops. And if I want to sort something into the y component, then y gives me mg cos theta. I also know that Fn is equal to mg parallel. Right? So technically, if I have something that's on an incline, right, and it's moving this way or it's moving that way, those are the motions. There's actually nothing happening here perpendicular to the surface. So technically Fn and mg perpendicular will kind of cancel each other as the object moves parallel to the surface. So they equal, these ones, they equal in magnitude but opposite in direction. So those are some of the things that we need to actually look at. The only time where you might need this, so this gives me F parallel and this gives me F perpendicular. So you've got your two forces. The only time where you might need this force of the normal is if you're ever working with friction. And we'll get to that as we get on. So technically, when I have an object on a surface, what I'm looking at is something like this. Now, here's my problem. When I draw a free body diagram, this is a force diagram. When I draw a free body diagram, I am not allowed to include this and the components at the same time. So if I'm looking at a free body diagram, I know that my object's natural motion is down, and that is represented by mg sine theta on an incline. I know I've got my force of the normal, that is parallel to the surface. I know I've got, so this is F parallel. I've got F perpendicular here, which is mg cos theta, which makes Fn mg cos theta as well. And then if the object has to go up the incline, then I have my force of friction here, and my angle theta is down here. That always forms a 90-degree angle. So your free body diagram options are as follows. If I want to draw a free body diagram for something that's free body diagram for something that's on an angle, this is how it's going to go down. The first thing I'll draw in is I will draw in my angle. Right, so this is option 1. Right, when you draw in option 1, you draw in your object and you show your force of gravity, which is down this way. You show your force of the normal, which is up that way. So I've got mg or fg here, and here I've got fn. Right, so that's your kind of setup. And you know that if you had friction, your force of friction would go there. That is how you would draw option 1. Now option 1 you only draw if you're planning to represent fg as fg. Your other option is, if I had my incline again and I draw my object, going up this way is my force of the normal. Great. Going parallel or equal but opposite but parallel to the surface is mg perpendicular, which is mg cos theta. Going down your slope here, you have f parallel, which is mg sine theta. And then going up the slope this way, you have your force of friction. Alright, so what you need to understand here, or what you need to grasp from these two options, is that I must never see. In option 1, I must never see your component forces. And in option 2, I must never see, that will be marked as incorrect, your force of gravity. So you can either draw one of these two diagrams, but you cannot draw your FG and your components on the same diagram, because that means that you didn't understand the question, or you're not grasping the concept of this object is on some sort of surface. So I would highly recommend, in my opinion, I would highly recommend that you draw option 2. Because option 2 doesn't just give you basic values. Option 2 actually gives you values that assist you in moving this object either up the slope or down the slope. And also, if I want to look at things like, if I want to work out force of friction, then I can go mu k is equal to Fn, and then I have that value for Fn. So it gives you more information that you may forget in an exam or test, but it will be better if you get into a habit of drawing this option 2 here. Alright, so let's move into the first situation. Alright, if I have a look here, we have a 50 kilogram skier, and this little skier is skiing, that's a mouthful, skiing down a slope, let's say down a frictionless snow slope. Right. This slope makes an angle. What am I doing? An angle of 30 degrees to the horizontal. The question is, what is the acceleration of the skier? Right, so that's our situation. So the first thing that you need to do when you have this kind of a setup is to actually draw out a free body diagram, or an idea of what's going to happen here. So let's just write down what I do now. I know that, so the information that I know is that I have the mu value sitting at 0 because there's no friction. I have the acceleration, which I don't know. I need a force, which I don't have, right? I know the mass is equal to 50 kilograms. So that's my information that I do know. So when I go and I draw up my free body diagram, let's just see what I have here. So I've got my object and it's sitting on some sort of incline. And going up from the surface, my skier has a force of the normal. Guys, when you're drawing these, please use a ruler. If you have no ruler, it is marked as incorrect. If they ask you to draw a free body diagram, it must be done with a ruler. Right. Coming down from the force of the normal is your, I'm just going to label it with the formula so that I don't waste time, is mg cos theta. Mg cos theta. And going down the slope this way is mg sine theta. So that's my free body diagram. There's no force of friction, so I don't have to stress about it. And now, in this situation, I know that the force of the normal and the mg cos theta here are not, your perpendicular force, are not participating. The only thing that is influencing the motion of my skier is my F perpendicular. So my force is F parallel, I mean. It's the force that is driving this whole system. So how does the skier get down the hill? Due to F parallel, because anything that's on a surface is going to want to go, an inclined surface is going to want to go down that inclined surface. So now I know that my force is actually F parallel. So if I come here into my calculations, I know that F net is equal to MA. Of this, I know my F net is mg sine theta. I know my mass is 50, but I don't know my acceleration. So we divide both sides by 50, so I'm going to have acceleration is actually equal to mg sine theta. Mg sine theta all over 50. I know my mass is 50. I know my gravitational acceleration is 9.8. Sine and my angle is 30. All of that over 50. Pop it into your calculator and you should get an acceleration value of 4.9 meters per second squared downwards. And there we go. So what you need to realize that in these situations, F net is all about what is driving it, because there's no force that's pulling or pushing. We're not doing work, energy, and power. Because there's no force that's pushing or pulling, this is the natural motion. It's the natural motion which drives the system down the slope. Right? So if something's just sliding, then I can take this mg sine theta as positive. If it's being pulled up, that's a different situation. We'll have a look at that now. Now let's have a look at example 2. Now example 2, it says you have a 50 kilogram man sliding down a grass incline which has a coefficient of friction of 0.2, which makes an angle of 30 degrees with the horizontal what is the acceleration of the man? Right, so that's your question. Now you've got to set it up. Now, a couple of things. The first thing you need to know is you need to decide which going up the slide or down the slide will be considered as positive. Because the natural motion of things is downwards, then in this situation, I'm going to show my marker that I'm going to take anything that's moving down as positive. That's the first thing. The second thing here is it says there's a coefficient of friction of 2. So in terms of my information, I know that mu, 0.2. I know that mu is 0.2. I know I've got an angle theta of 30 degrees. I know the mass of my man, which is 50 kilograms. And I need F net, essentially, and now I need acceleration. That's the main thing there. Now, once all of this sorted out, I need to understand that friction opposes motion, right? So, friction is caused by the normal force friction is caused by the normal force. In other words, it means it is caused by the weight of the object pushing down on the inclined surface. Right? So now my biggest problem here is F net, because when I draw my free body diagram, I know that I have a force of the normal. Great. I know that in the opposite direction there I have mg cos theta. Because I'm on a slope, I know my natural motion is down, which is mg sine theta. But because of this coefficient here, this mu being 0.2, I also know that going up the incline, I have a force of friction. So that is my free body diagram. And like I said, you need to make sure that you draw this with a pencil and a ruler. Right, now I've got my object, and my object can slide down, but something's resisting it, which is force of friction, which means in terms of F net, I have a forward situation, which is F parallel, and I have a back situation, which is force of friction. So in terms of F net, I can either sort it out separately or all together. So I'm going to do both, and then you can see which is your one. So if I had to say, I know I'm using F is equal to MA. That's my formula. F net is equal to MA. Over here, it's still F net is equal to MA. All right. So in terms of F net, I can say my forward force minus my backward force. All right. My forward force is mg sine theta. And my backward force is the force of friction. And the force of friction formula, because this whole system is moving, is mu k. Let's just get an eraser here. Oops. Mu k times Fn. So my mass is 50 kilograms times 9.8 sine 30 degrees. Oops. 30 degrees minus 0.2 times mg cos theta. Right. So my forward was the force going down, and my backward was my friction. All right. So I'm going to end up with a situation where it's 245. Minus 84.8704, etc. And then you get F net at 160.1295104 newtons. Note, do not round off. but you can keep it in a fraction or third form if that is the situation. And then I've got F net here at 160. Put it in substitute into my formula 160.129 and so on. The mass I know is 50 times the acceleration here, and then acceleration is equal to 3.20 meters per second squared downwards. And there's my final answer. Right? Or you could have said F net is equal to MA, and you could have said mg sine theta, or rather, let's put it like this. You could have said force applied, which is that downward natural force, minus force of friction equals MA, mg sine theta minus mu k times Fn is equal to MA. We found this at 245 minus 84.8704, etc. is equal to 50A. And then A is equal to 245 minus 84.87 divided by 50, and you still get 3.20 meters per second squared downwards. So that's what I meant by, if I look at this too, you could have done this separately, or you could have just brought it there. Either way, you still get the same amount of marks at the end of the day. Right, let's have a look at the next one. The next thing we're going to look at is pulleys and inclines. Pulleys and inclines with masses hanging over and so on. And example 9. So we look here. It says a 5 kilogram mass is placed on a frictionless incline which makes an angle of 30 degrees with respect to the horizontal. A rope is attached and positioned over a massless frictionless pulley at the top of the incline, and a 6 kilogram mass is suspended from the free end. So I would suggest you write down the question and draw up this pulley system. I've got your mass 1 at 5 kilograms and mass 2 at 6 kilograms. They also want the tension. So I'm going to say that's T1 and T2. And they've given me an angle of 30 degrees to the horizontal. And my mu value is 0 because it says the incline is frictionless. Alright, so the first thing we need to understand about this thing that we're dealing with is that if it is attached by some sort of rope, then when I look at it in essence, it is one system. We spoke about this. If they're touching in some way, we must understand that there is one system. And if there's one system, it means there's a total mass. So M total is equal to 5 kilograms plus 6 kilograms, and we end up with a mass total of 11 kilograms for our calculations. That means that if the system has a certain acceleration, that means each mass individually has that same acceleration. So when I have an inclined system, I need to make sure, the first thing I need to do is I need to choose what I would consider a positive direction. Now, because there is no friction, and I said this before when we spoke about the other examples, I have to think about what I would consider positive. So I know that the second mass here, M2, is going to drive this whole system. So the positive direction is over the pulley. So that's how I know acceleration is going to be positive. So I can say that acceleration is positive, right? Acceleration is positive in terms of this motion. That means if M1 moves upwards, so up the incline or to the right, then it would be considered a positive move. If M2 moves downwards, right? That's considered positive. So M1 can move in that direction and over the pulley, and M2 can move in that direction, and they'll be considered positive if those are their motions. Right. The other thing that I must check here, there's my theta value, so I should write that down. Theta is equal to 30 degrees. Now what I need to sort out is, what does my free body diagram look like for something like this? Now, another thing that I should tell you about choosing this positive direction, if you choose this motion as positive, then that's fine too. Just make sure you sort your calculations out, just all the same, right? So in terms of a free body diagram, please make sure that you use a ruler. This one's done a little bit differently. So the first thing that we do here is we draw our mass, and I know that my mass is attached to some sort of pulley, which will be somewhere there. Alright, so the first thing is, I know it's on a surface, so I have f of the normal here. And I know that in line with that, I have mg cos theta. I also know that the natural motion of this M1, right, M1, I just label that, is down. F parallel, or rather we can say mg sine theta. Remember the natural motion, right? This is the natural motion, but because we chose over this pulley system as positive, then we can already see that we're going to have a little bit of a situation. All right, this whole thing, we've got a force applied. That's going to do that. Your force applied, that goes over this pulley, and we've got our second mass here. It's got a tension there, F tension or F applied, and what's happening as it comes down this way, we've got M2G. So this first one for mass 1 is going to be M1G sine theta and M1G cos theta, and for this one it's M2G. Right, and this here is your driving force of your whole system. Right, so M2G is going to push this whole system into a positive acceleration. So this M2G is our forward force. Now, if I look at the other one, the natural motion of the object is to go down a slope, which makes your F parallel opposing that sort of motion. Right, so in the end here, I want acceleration, which I don't have. I need an F net, which I don't have yet, because there's two forces, a forward and a backwards. I have theta, which is 30 degrees. I know I said mu is 0. I've got my mass total is equal to 11 kilograms. Right, and the formula that we're using here is then F net is equal to MA. Right, now F net, I can see that there's a forward force here and there's a back force over here, which means I need to sort out F net. So I'm going to say F net is equal to M2G minus M1G sine theta, which is equal to M mass times acceleration. All right, M2 in this whole thing is 6, G is 9.8, minus M1, which is 5, multiplied by 9.8 times sine 30 is equal to the mass of my whole system is 11 kilograms multiplied by acceleration. Divide both sides by 11. So I've got on this side 58.8 minus 24.5 is equal to 11A. Or I can say 34.3 let's do that. 0.3 newtons around that point is equal to 11A. Divide both sides by 11, and A is actually 3.12 meters per second squared. And that is how we calculate the acceleration of an inclined plane sort of system, which means that this part here is 3, that's sorting out your F net, and then 4 is calculating your acceleration in this whole situation. The next thing they want is T1 and T, or the tension in the string. So when I think of tension, essentially, I know that T1, which is here, is equal to T2, which is there. The reason, because they share a string, right? Because they share that string, those forces should be equal to each other. So remember what I said the last time. When you work with these, work with the thing that has the least amount. So M1G has this one, and it has that one, 2. And this one also 2, right? So either way, you could work with either one. I'm going to work with the one that's accelerating down. So what I'm working with is this sort of setup of M2G and T2. Right, essentially here in this whole thing, I want us to remember our formulas for if we're working with the mass over the pulley. So this only works for mass over pulley. In the previous video, you've seen the two formulas. So if I have mass over pulley and the mass is going down, then it's T is equal to M2G minus M2A. If this mass is moving upwards, then tension is equal to M2G plus M2A. So now if I look at this M2G, it's moving down. So that's the formula that I'm going to use, or the acceptable one. So therefore I'll go T is equal to M2G minus M2A. M2 is 6 times 9.8 minus M2, which is 6, times acceleration, which is coming from there at 3.12, don't round it off, is equal to 58.8 minus 18.72, which then gives me 40.08 newtons. And that is the value of the tension. So therefore, the tension in the string or rope is equal to 40.808 newtons downwards. I make it very clear. What I like to do is highlight that final answer always. Whatever answer you really want your marker to focus on or mark, I would definitely suggest that you make sure that you highlight your answers or make it very clear where your final answers are. So that's how you answer a pulley system on an incline without friction. So obviously the next one I'm going to do is one with friction, and let's have a look at that. Alright, let's say we have the following little system for the last, well, not the last, I'm going to do one more thing after this, but this is your last pulley question. I've got an 80 kilogram box of bananas, and it is placed on an incline which has an angle of 30 degrees to the horizontal and a coefficient of 0.45. A rope is attached in position over a massless frictionless pulley at the top of the incline. A monkey which has a mass of 100 kilograms hangs over the pulley. Calculate the tension in the rope. Right. So here's what we've got. Just write down all of our information. because this is one system, I have a total mass, right? Mass total is going to be 80 plus 100, and that's 180 kilograms. So that's sorted out. I do have a mu value, and that value is 0.45, which means if I have friction, I need to work out the force of friction, which is going to be mu k times Fn. I then also know that I've got a theta value which is equal to 30 degrees. And in this whole thing, they want tension. Oops. Now, I know tension has two options. I either have a tension that moves downwards or hangs down or moves up, or I can work out the tension on the incline, which goes down the incline or up the incline. Right, so those are my options. When I'm looking at something like this and I look at my tension, for example, please make sure you're getting these questions down, these diagrams down, so that you have some sort of idea of what's going on. Alright, so in order to work out tension, I can either work out the tension of mass 1, tension of mass 1, or tension of mass 2. Those are my options. Now, I prefer this one, mass 2, the monkey, right? Mostly because it's easier to do the calculations and I don't have to worry about what's happening on the incline, especially when it comes to friction, right? So I'm going to use Tm2, which is M2G minus M2A. That's my setup. But my problem in this whole thing is I have mass 2, I have G, I have mass 2, I don't have A. So to get to this, to finally substitute into this formula, I need to find the acceleration. Now the only way to find the acceleration is if I go F net is equal to ma. So I first need to do this whole little chunk of information before I get into actually doing what I need to do. Alright, so let's have a look here in terms of F net. In terms of mass, I know my mass of my system is 180 kilograms, but I don't know F net. Now I need to sort that out. So I need to decide what's my driving force of my system and what's being pulled over. So I'm going to draw a free body diagram to get that sorted out. So in terms of my free body diagram, I've got my incline over here. I've got force of the normal there. Let's just take that there. I've got a pulley there. I've got mg cos theta over here. And I've got my F parallel, which is mg sine theta, doing that on that object. Also got a string that's going up here, so I've got a force applied. Right. And going over here, I've got my second mass, which is M2G. And I've got a tension that's moving like that. But more than everything else, I remember I have friction. Now, friction will oppose motion. So before I put that in, I need to decide what's my positive acceleration. So I'm going to say that this is, for me, acceleration is positive. And you can indicate it like that on a free body diagram, or you can just indicate to your marker, this is my forward situation. Now, if I look at M1 and I know I have friction, friction will oppose this motion, which means friction has to go, do another color, friction must go in this direction, which means something that is going to aid my F parallel. So I must draw in force of friction there. So that is how, remember, you can use a ruler. It looks a little bit better than mine. That is what your free body diagram is going to look for this situation. So if I look at all forces acting on M1, M1 has, going down the slope, it has mg sine theta, and it has the force of friction. Right, that's pushing it down. And then going up the incline, it's got M2G that's pulling it, or it's the driving force. So I've got a forward force here for my system, and I've got 2 backward forces. All right, so now I need to sort out F net. So I'm going to do it all at once, and I need my acceleration, and I need acceleration. I don't have either one of those values. So I'm going to say F net is equal to MA. And at this point, I've got one forward force, which is M2G. M2G, right, minus mg sine theta plus force of friction, which is equal to mass times acceleration. Now my force of friction formula is a mu k times Fn. Now my Fn, if I look at my free body diagram, lines up with my perpendicular. So Fn is actually mg cos theta. So now I'm going to take all of that into consideration. So if I'm looking here, I'm going to go m2g minus mg sine theta plus, put this in brackets, mu k times Fn, right? And the Fn that we're looking, I'm just going to put it here, Fn, which is technically mg cos theta, I just said that now, is equal to mass times acceleration. So now let's put some values in here. I've got m2, which is 100 times 9.8, all of that, minus mg sine theta, which is 80 times 9.8 times sine 30, plus mu k, which was 0.45, times mg cos theta, which is 80 times 9.8 cos theta, is equal to the mass of my system, which was 180 times acceleration. Right, essentially I've got 980 here minus 80 times 9.8 sine 30 is going to give me 392 plus 0.45 times 80 times 9.8 cos 30 is going to give me 305.5337, etc., which is equal to 180 acceleration. Now I'm left with 900 minus this bigger bracket here, and I've got 282.4663, which is equal to 180 acceleration. Divide both sides by 180, and I'm left with an acceleration which is equal to 1.57 meters per second squared. Oops. In the direction of motion. Alright, so now I've got my acceleration, and I can finally put it into the formula that matters to me here. So basically this value here tells me that M1 accelerates at 1.57 meters per second squared up the incline, and mass 2 accelerates at 1.57 meters per second squared downwards. Alright, so that's the information that I've got now. Now they need tension. So I'm going to say T2, or tension, is equal to M2G minus M2A. Right? I know my second mass is 100. So 100 times 9.8. Oops, times 9.8 is minus 100 multiplied by 1.5692. I'm taking that value, but the not rounded off one. So I'm left with 980 minus 156.9257222, etc. And I'm going to end up with 823.074 something. So it's going to be 8.07 newtons. And therefore, that is the tension in the string that we're dealing with. Right? So this is your applied force that's driving this whole system, or whatever the case is. If I wanted to do a check, I could do a check. And how we would do a check is we'd look at the tension on the mass that's on the incline. So the formula for that is T is equal to M1G plus MA. Now M1G, right, is actually pulling this mass down that incline. And something else that's also, which gives me mg sine theta. And there's another force that's assisting it, which is the force of friction. So this M1G is mg sine theta plus my force of friction. So if I look at that, I'm going to say mg sine theta plus, I'll put it in brackets, mu k times Fn plus MA. Now mg sine theta would have been 80 times 9.8 sine 30 plus mu k, which is 0.45, times mg cos theta plus m, which is 80, times the acceleration, which is 1.5692. Right. So that's now going to give me 80 times 9.8 sine 30 is going to give me 392 plus mg cos theta, which is 305.5337. We did this because this was the backward calculation. See, it's up here. All right, answer with that, plus 80 times 1.5692, which is 517. Oops. 517.536, and then that equals to, if I add all of that stuff up together, I end up with 823.0697, which is going to be 0.7 newtons. So that's T1. And those two values, that was T2. These two values should be exactly the same. Now, can you see why I only worked with T2 rather? Because there was less calculating that needed to be done. With this one, there was, so much that needed to be done. It's just unreasonable. So work with the force, or work with the tension that has the least amount of values that you actually need to deal with. Right, that's the last thing. Please make sure that you get all of this into your books, that you go through these types of questions, go through the worksheets, ask for solutions. That way you can see if what you're doing is the right thing or not the right thing.